So, like I said, thanks so much for coming to this. This is my latest talk. Everything you've learned about SSL is deprecated. And it's a new kind of topic for me. Usually I talk about JavaScript and the web and how JavaScript is awful. If you're coming to the party tonight, I have a whole game show thing that I'm doing about JavaScript being awful. But today, today I'm going to do a real talk about SSL and the security infrastructure of the internet. Because there's a lot changing in this space right now. I've been fascinated with what's going on in this space, how things are evolving. Everything is different in the last 2 years. And you would not believe the things I have learned moving from the web into this space recently. It's a weird world. And I'm coming from JavaScript, and I think it's weird. So it's really weird. OK, 25 years ago, when I was first starting out, I learned how to secure my first website. And to do that, I needed a certificate. And this guy from a certificate authority was happy to sell me one. It felt a little bit like paying protection money. It's a nice website you got there. But first, in order to get that certificate, I needed a CSR, a certificate signing request, and pay some money and get that certificate. So how do you generate a CSR? Well, of course, I went to StackOverflow, and I found the canonical question of, how do I make a CSR? Who learned how to make a CSR for the first time by going to StackOverflow and copy and pasting this? Yeah. The trouble is that this is still like the answer if you go to StackOverflow now and type, how do I make a CSR? The trouble is that every part of that command is wrong today. Let's break that down. OK. So the command starts with openssl request new key. Well, that part's fine, because we're still requesting a new key. But then it says, well, I want an RSA key with 2048. And that's not a good idea. You shouldn't get an RSA key with 2048 anymore. And it says SHA-1. Oh, and you definitely shouldn't get a SHA-1 key. And it will say 3 years. I miss 3-year certificates. You can't get those anymore. The rest of it is all right. But like, a core important part of that command that we're still copying and pasting from Stack Overflow is wrong at this point. Everything is changing right now in this space. Certificate automation is coming, and it's going to blow up this old protection racket that existed. The good news about how this is going to work is that you don't have to pay anybody any money anymore. The bad news is that everything you know about how it worked is different now. And there's work that we're all going to have to do over the next couple of years. But before we jump into that, you might be wondering who I am and why you should give a crap about that and why I've spent all this time learning it. Currently, I'm the CEO and co-founder of a company called CertKit, Certificate Automation, which is why I've been spending all of my time learning about how this stuff works. Previously, you might know me for other things that I've built, request metrics, web performance, Track.js, JavaScript error monitoring, and then I host JavaScript Error Game Show and PubConf and do various other silly things on the internet. So here's how today's talk is going to break down. Well, first, is this weird? This terminal thing that I built, is this fun? All right, cool. Usually I'm boring and I just use PowerPoint, but like I wanted to kind of do something like silly and terminally. So I built this thing with Reveal.js. Claude built this thing with Reveal.js based on my instructions. And I think it turned out really good. I'm going to just go show, you probably can't see it, but down here in this corner, I have this little switcher because I have dark mode. But it's not as easy to see in the back. All right, anyway, moving on. Not the logistics of presenting. So we're going to talk about how it used to work, how SSL used to work back in the day, and then we're going to talk about all the things that happened that made it break. And then we're going to talk, finally, about the new way that things are going to be and how we're going to move forward. So first, let's start with how it worked. The SSL handshake, the original SSL handshake. It starts with your browser saying, hello. I speak some version. I speak SSL 3. And here's some ciphers. Here's some secret decoder rings that I have that I can speak with. So there's one. There's 36 more of them. There's a ton of them. The user picks one and says, hey, let's use this one, and returns a certificate to prove that the server is who it says it is. Your browser grabs that certificate, grabs the public key, and generates a pre-master secret that it's going to use to encrypt communication. And it sends that secret out over the wire. And then that secret is used to encrypt future traffic. And that's how it worked back in 1999. But let's take a closer look at the parts of that. First, the certificate. The certificate starts with a subject. Here's who you are. And then the issuer, who signed it. Who's going to vouch for you? Who's going to prove that you are who you say are? The date ranges for how long it's valid used to be 3 years or even longer. And the algorithm used to sign the certificate, how the public key is encoded. So much of this isn't this way anymore. So how does your browser know to trust that certificate? Well, it checks a chain. There's some math involved where it derives this, or the certificate is generated and can be linked to the other certificates that have signed it. So your certificate on the bottom was signed using SHA-1 by an intermediate CA, which was signed by a global root. Now, you didn't choose that global root. That wasn't anything that you did. That got included and bundled with a web browser to say, hey, trust everything that comes from DigiCert or whatever. If that chain all checks out, you get a green padlock and everything feels safe. If not, you get Chrome's scary warning page, your connection's not secure. You might have noticed that I've been highlighting the term RSA in red everywhere. And that annoys the crap out of me because every time I've used RSA, it's been in a different context. It means a different thing every single place I put it. RSA, in fact, doesn't mean anything. It's just the acronym of these three dudes' names who really liked naming things after themselves. RSA shows up in security everywhere because they liked naming things after themselves. So there's RSA, the key exchange, which is not secure anymore. There's RSA as the certificate key, which is being phased out by elliptic curve. There's RSA, the signature algorithm, which might be okay, maybe. There's RSA, the conference, which is in San Francisco, costs about $2,500. And there's RSA, the company, that took $10 million from the NSA to build in a backdoor into their products. So when you say RSA, you could be talking about any of these, and there's actually a couple more. But these are the big ones that people are usually referring to. All right, let's talk about certificates again. Because there's 3 different levels of certificates, 3 different levels of saying you are who you say you are. And the simplest one is domain validation. It's like, hey, I'm going to issue this certificate. You prove that you own example.com. I can vouch for that. Good to go. DV proves you control the domain. Costs about $200 a year if you go to like a reseller today. Organizational validation. Now, if you try and purchase an organization validation, they might call you and make sure that you answer the phone and do a Dun & Bradstreet lookup to make sure your company actually exists. And to do that, you'll pay $500 a year. And if you really want the best validation, you can buy extended validation for $1,200 a year, which adds a bunch of extra paperwork. And it used to mean that you got a fancy green thing in the URL, or in the URL bar with your company name. Now, you don't get that anymore. But I pulled this graphic off of an SSL reseller yesterday, who apparently still thinks that that's important, that you get that. I'm not sure how they can get away with that. All right, so how do you get into this racket? How do I get away with selling files for $1,200 a piece? Well, you have to get your root cert into Chrome. And how do you do that? Well, you need to get audited. You need to get audited once a year for a standards compliance called Web Trust. And if you passed your audits, that was good enough for Microsoft and Google and most of the other browsers to include your root certificate and you're in. But you really only needed to look good for your audits once a year. And you picked who your auditor was. And you paid that auditor. And then you chose whether they were going to be your auditor next year. I'm not saying that it's corrupt, but it's at least a little suspect, right? The incentives were a little wrong. And in 2005, all of the CAs, all of those people who were paying their own auditors got together and held a sit-down in New York. And they called it the CA Browser Forum. They wanted to create a board where they were going to self-regulate to create a simpler and consistent set of rules that they were going to operate. Honestly, I started down this thing where I was going to compare CAs to mobsters, and the thing like literally writes itself. Like they literally had a sit down in New York to fix their rules for themselves. I don't know how this all came to exist. It's crazy. The whole thing feels straight out of Godfather. Okay, here's how that worked. The CA Browser Forum. It's a self-regulating body where the CAs and the browsers all get together and agree on their set of rules. Those rules are called the baseline requirements. And it's a rule book. It's like, here's the set of things about not being grossly negligent that you're going to need to follow in order for our browsers to trust you. If you want to change that rule book, you have to get all of the CAs to agree. The browsers couldn't change any of the rules without the CAs supporting them. Now, each browser did have its own root program, its own personal set of requirements, like Chrome and Internet Explorer, and everybody had their set of rules that you have to follow. But those rules at this point were basically, pass your web trust audit, follow those rules, you're good to go. So that was the deal. That was the deal in 1999. You want to be secure, you pay your money to the CA. They verify that you can click an email link, and they give you a certificate. Certificates were valid for 5 years. The certificate they gave you was valuable. Like if you lost it, if it became exposed, you had to pay for a new one. And the CA Browser Forum governed changes. That was the theory, anyway. Today, that's not how any of this works. But let's talk about the story about how that fell apart. So we're going to break this down like we're going through a log file. Event by event, disaster by disaster, how this whole situation came crashing down. In 1999, SSL 3.0 became TLS 1.0. It was mostly just renaming it. There was a few tweaks in how things worked. They changed the names of the cipher suites from SSL underscore to TLS underscore, but they were basically just renaming it. But we haven't called this SSL since 1999, and yet you all came to a talk in 2026 called Everything You Learned About SSL is Deprecated, because nobody calls it TLS. Everybody still calls it SSL. It changed a bunch over the next 20 years. In 2006, TLS 1.1 fixed an initialization bug. And in 2008, 1.2 added a bunch of modern ciphers. But almost nobody upgraded. Everybody still calls it SSL. In the early 2000s, most people were still running SSL 3.0 or TLS 1.0 and had not upgraded. In 2011, we start seeing the biggest cracks. The first one is DigiNotar. Has anybody heard of this story? One person, 2 people, cool. This was a big one. So this was a CA, a Dutch CA, and it got completely compromised. Attackers got in via a web server, and they pivoted to the CA root source. So they got to that root certificate. And they issued a rogue certificate for google.com with it and put it in Iran. It was likely an Iranian government action, but nobody could prove it. But like, who else is going to issue a rogue google.com certificate and put it in Iran? What they found was that a CA was full of unpatched software. There was no network segmentation, internet exposed internal services, default passwords, but they had passed their audits. Their auditors, which they had hired and paid for, had passed them. After this, DigiNotar was bankrupt within months. Everybody distrusted them. A few years later, Edward Snowden, who remembers this? This was big news, right? Yeah. Revealed a massive worldwide surveillance operation from the NSA. Since 2007, they were recording all the encrypted traffic on the internet. And then they thought, if we can record this traffic and then steal or compel a company to give us the private keys later, you could decrypt all of the traffic retroactively. Now this was initially done with a project called Prism, where they had partnered with the big technology firms, Microsoft, Facebook, Apple, et cetera, to basically get a copy of all the data passing over their networks. Later, Project Tempora, with the help of the UK, hooked into the baseline backbone fiber optic cables and just started recording the whole of the internet. Now, this wasn't just the United States. It's often just blamed. I'm American, and so we often get blamed for this, but this actually wasn't American. This was Western intelligence. Everybody was in on it. Canada was in on it too. What this proved is that we were recording this thing for the purpose of intelligence and counterterrorism and stuff like that. This all came to light that we're doing it. But I'm sure everybody else was doing it too. I'm sure the Russians were doing it. I'm sure the Mossad was doing it. I'm sure Iran was doing it. This was a concept, and we could probably do it bigger than they could, but everybody could record all of this traffic. What the documents revealed was that the idea that we can harvest this data now with the goal of decrypting it later was a real thing. It was something that could really be done. It wasn't just an academic theory. There were billions of dollars thrown into actually implementing this idea. So how did we deal with that? Apparently, we brought up our emojis is how we deal with that. Sorry. Cool. So how did that work? Well, here's our SSL sequence. Now, this specific place here is what we're talking about, in the client key exchange. Now, how this would work is the client would get the server's public key and generate a secret that they would use to encrypt all future data. And it would pass that secret over the wire. Now, if you could ever get the server's private key, you have already recorded the master secret, and you can now decrypt all of the data. The private key was precious. The private key was sacred. If you had the private key, you could decrypt all the data that had ever been sent using that certificate. Because the old handshake here was using the same long-lived private key for two things. It was using it for identity to prove it was who it says it was, but it was also using it for encryption. And that was the fundamental design flaw. So in 2013, we fixed it and came out with Perfect Forward Secrecy. Perfect Forward Secrecy was the direct answer to this problem in the NSA leaks. And it splits those two jobs. The certificate itself still proves the identity. It's your ID badge. It proves that you are who you say you are. But encryption, actually encrypting the data, shifted to using one-time keys, generated new every single session, using Diffie-Hellman, which we'll talk about in a second. A stolen key, after you have private forward secrecy, can no longer decrypt your past traffic. And this totally changes kind of the severity of leaks. If you lose your private key, it's bad, but it's not the end of the world anymore. Somebody could potentially impersonate you, but they can't get at the raw data of all of your sessions anymore. It turns it into, it makes automation, it makes passing private keys around in secure contexts much more feasible. Let me take a very brief detour into math. This is the only real math slide, I promise. Okay, I said Diffie-Hellman. How does that work? How can you generate a key that's only useful once and not have something float over the wire that everybody can just read and the NSA can do it again? Well, the client and the server both generate secrets, A and B, using the ciphers that were negotiated. An observer on the wire, say the NSA, can see the value of G to the A and G to the B move over the wire. These G and P values are like predefined known values. But you can't see what A or B was, just the results of these computations. Now, because of math, both sides having the other value can arrive at a value of G to the AB. Now, because they can both compute to this value, but neither side could compute it knowing only their data, this becomes secure. And this is called a discrete logarithmic problem. It's computationally infeasible for somebody to see these values and figure out what the ultimate key was. It's still the same shared secret, but neither side sent it. The observers can see these two intermediaries, but they couldn't compute that new value in any sort of practical way. And so that's what forward means in forward secrecy, is that you could no longer use the data that you recorded to decrypt something in the future, because the private key wasn't used anywhere in this. The private key was not a part of the algorithm to generate the encryption key. 2013 was a big year. A lot changed. In 2013, a lot of CAs had gotten compromised. We already talked about the Iranian thing. Komodo, Turk Trust had similar incidents, maybe less big. The whole CA model of trust was starting to fail. And a lot of times, Google was the one getting screwed. Google, like false certificates for google.com were getting generated. And so Google wanted to fix this. And they couldn't trust the auditors for some reason. So they said, you know, let's not rely on that anymore. Let's start logging all of this. And so they published RFC 6962, where they said, we're going to have a certificate transparency log. Every certificate that you issue, you have to provide in a public append-only log. Every single CA. You all have to do it. And that way, anybody, especially Google, can monitor what all the CAs are doing, like when a google.com certificate is issued. Now, they didn't get the CAs to agree with this. They just showed up one day and said, you know what? To improve the security of certificates, Google Chrome is going to require certificate transparency for all EV certificates starting in 2015. It was later expanded to all certificates in 2018. Basically, they said, you're going to have to log all of this, or you're not going to be trusted in Chrome anymore. And this was one of the first real big moves against the CA browser forum that says, no, we can't trust you anymore. You're not changing the rules fast enough. You're going to produce CT logs, or you're not going to work anymore. And at this point, Google Chrome was big enough that that was actually a real threat. The CAs didn't volunteer for this. They weren't ready. They didn't get approval. You should focus on preventions, on improving auditing, not logging. Folks like Symantec were saying that at the time. Chrome didn't ask, they just added it. How does that work? Well, so there's a few places where you can check certificate transparency logs on your own. There's one of them on my website, certkit.io. You can hit tools and go to CT log search. And it looks like this. You type in a domain name, and you get a list of every certificate that's ever been issued for that domain, which is actually really cool. You can see what domains they're asking for, who issued it, when it expired. You can basically enumerate every domain that a company has, public or not, using certificate transparency logs, which is kind of cool. Also kind of terrifying. You can go and search, like if you search army.mil, which is the US Army, they were issuing, up until recently, public certificates for individuals. So there's a bunch of email addresses for Army officers in the certificate transparency logs. I don't know if they know that, but I think it's kind of cool. I imagine they get a crap load of spam. Okay, so that's the certificate transparency logs. We're still in 2013. Lots is happening in 2013. SHA-1. SHA-1 is a hashing algorithm, like MD5. So if you take a hash of SHA-1, you put a really long string into it, like say the guts of a certificate, and you can generate a shorter hashed version of it. Now, in 2015, in 2005, research was already saying that, hey, this isn't actually very good. We're going to get collisions. There's like enough data being pushed through this that we're going to get a collision. A collision is that we have two different long strings, two different potential certificates that would generate the exact same hash. How does that work? If we go back to the certificate chain, SHA-1 was used to sign those certificates. So if I have my certificate for example.com, SHA-1 was the thing that proved that it was signed by the DigiCert intermediate and the DigiCert root. If I can build a certificate in such a way that I could generate a collision, I could build two certificates a normal certificate for mydomain.com that happened to have the same SHA signature as a cert for google.com. And if I pass that up to an intermediate and get it signed, the CA has generated an invalid certificate and has no way of ever knowing. It wouldn't show up in the logs. Now this, supposedly was all theoretical. And that's exactly what the CA said. This is theoretical. This isn't actually ever going to happen in real life. We're not going to change anything. Microsoft in 2013 said, this isn't theoretical. This is actually like a critical error. And they now took their first big move and said, we're not going to trust SHA certificates after 2016. Again, they didn't ask for approval. They just said, if you want to work in Windows, which you want to work in Windows, you can't use SHA-1 to sign things anymore. The CAs obviously complained, we're not ready. We have enterprise customers that can't do it. In 2015, so again, coming from the web into learning more about the security space, they have the best names. They come up with crazy ass names for the kind of stuff that they do. Like, I wish we came up with these fun names for like losing the value of this in JavaScript. Like, we don't have anything like that. The left padding wasn't a thing. In 2015, the shappening, were the first free start collision, where if you could just control everything about how the certificate started, you could generate a collision. And then in 2017, Google proved out with Shattered, generating a full real collision of SHA-1. 2013, Microsoft said this was going to happen. It stopped at 2016. In 2017, it happened. But at this point, we were generating 3-year certificates. And so there were SHA-1 certificates out there in the real world, fully trusted, until at least 2019, when collisions were already proven to exist. This was one of the first black eyes against our mobster CAs, and kind of made them look pretty bad in having dragged their feet on this issue for so long. In 2014, we had Heartbleed. Did anybody have to respond to Heartbleed? Did anybody have to revoke certificates and regenerate everything in the panic? Heartbleed was a buffer overflow in openssl, where you could send a malformed request to a server, and you got back 64 kilobytes of random memory, whatever was in RAM of that server. Like, it could be private keys, it could be session tokens, it could be passwords, and you could just do it again and again and again and get 64 kilobytes of data back, whatever was in there. 17% of the internet secure servers were vulnerable to it. It was a catastrophic failure. But it was two different stories, because some of the internet had already implemented Perfect Forward Secrecy. And if you had Perfect Forward Secrecy and your private key leaked, that was bad. But it's not like anybody could use that key to decrypt your past data. You lost whatever was on that server at that moment. You had to regenerate your certs. You had to change your passwords. But you didn't have to figure out how to handle 10 years of lost data. If you didn't have Perfect Forward Secrecy, you had to assume that everything that you have ever done to that company was now public knowledge, was now exposed. Every communication that you'd ever sent, even if it wasn't during this particular window. In the wake of this, hundreds of thousands of certificates had to be revoked. Everybody who was affected by this, every certificate needed to be revoked. And the infrastructure could not handle it. It was obvious that revocation was actually broken. You actually can't revoke a certificate super reliably. How does revocation work? Well, at the very beginning, we had certificate revocation lists. So as the certificate authority, every time a certificate was revoked, it went into a big text file. Here's a list of every single certificate that's ever been revoked, which obviously is not going to be a solution that scales. It grew huge, it was slow, it was stale, almost nobody looked at it. So in 1999, they came up with a new way, which is the Online Certificate Status Protocol. Basically an API that you could call and say, hey, is this certificate valid? Seems like a better solution maybe, but it wasn't very reliable. Those services often went down. CAs were not super good about keeping them online. And there was a big privacy aspect of it of, do you want to, every time you visit, say, some website, do you want a call being made saying, hey, is the cert for this some website being like okay on a different request? You're essentially revealing all the traffic that everybody is doing through the OCSP requests. So to handle that, we came up with a brilliant idea in 2003 called stapling, where we were just going to include the results of that for every single TLS request. The problem is it was just too hard to implement, and so nobody did it. And so in 2012, Chrome says, all right, nobody's going to do this thing. It turns out that this, although well-intentioned, is a stupid idea. Because the online certificate status protocol was a seatbelt that snaps when you're in a crash, is their direct quote. Is like, it's great, it works every time except when you need it. When you need it, you have an attacker that blocked the request. And so it was treated as default open. Or you have you've revealed that something happens. So instead, they implemented something called the CRL lists, which included about 1% of the revocations, only the high priority ones, only the things that were super important. Mozilla, Microsoft, and Apple have similar programs where they have a subset of the total number of certificates that have been revoked, and they include it with their browsers or operating systems. The problem with that is that it doesn't work. So if you go to revoked.badssl.com, here's an example. So this is a site that every few days it gets a new certificate, and then it revokes that certificate. And on any given day, on any given hour, you go visit it in different browsers, and some of them will load it fine, and others won't. On this particular day, Chrome blocked it. But Firefox and Safari both loaded it. If you load it right now, it might work. It might not. The problem is that there's no definitive thing that says, hey, I revoked this certificate, and now everybody's going to block it. There's too much indirection in the process, and people don't know about it. What, did you just go to it? Did it load? What browser did you use? Edge, all right. So yeah, whether or not the revoke certificate for this makes it into the browser is meh, maybe it'll work, which meh isn't really a good strategy when you're trying to deal with I gotta stop an exposed certificate from being used. The certificate system for revoking has kind of always not worked great. And they've kind of always known that. The CA Browser Forum's own conclusion is that revocation's kind of broken, but we don't know how to fix it, so we're just gonna kind of keep going. In 2015, a project called Let's Encrypt started. Josh and Eric were working on a free automated certificate authority at Mozilla. And Alex and Peter at EFF were working on a certificate issuance protocol. In 2015, in 2013, they kind of found each other, and they formed the ISRG as a nonprofit. The ISRG is the company behind Let's Encrypt. The ACME, the protocol, which is an automated mechanism to get certificates, and Let's Encrypt, the CA, are two sides of the same project. They had this vision of, we can generate a way to build free certificates that are only valid for a short period of time, so revocation's not a problem, and automate the process end to end. At the time, getting a certificate meant you had to go to a CA, and you had to fill out a form, and send in your certificate signing request, and you'd pay your fees, and they would do some work to verify you, and you'd get your certificate in a few days, and that certificate would last for years. The ACME system was a fundamental challenge to how that was going to work. Here's how ACME works. So you have a client, you have a web server, and you want to get a certificate. And so you go to your CA and you order a certificate for star.example.com. And the CA with ACME returns a challenge. Prove to me that you control example.com. Now you can prove that in one of two ways. There's a couple more ways actually, but these two are the majority used. You either put a DNS text record at acmechallenge.example.com, or you host a file on well-known/Acme Challenge. And if you can do one of those things, it proves that you control that domain, and you're validated. And then you send your certificate signing request, and you get a certificate. No human in the loop, no phone call to verify that you are who you say you are, no payment. The entire flow is machine to machine and happens in seconds. The idea was free certificates, short lifetimes, fully automated. The CAs hated it. Enterprises are never going to be able to handle this. We're not going to be able to replace all of these processes, is what they were all saying in 2015 when this project started. In 2017, Google, in response to all of the leaks and understanding revocation is broken, proposes, you know what, we should lower certificate lifetimes to 1 year. At this point, 3 years was the standard, which meant when SHA-1 changed, and even when you hit the deadline, you still had to wait 3 years for those old certificates to fall off and become invalid. Google proposed dropping it to 1 year. Make a revocation not a problem. We'll get rid of things. The browsers all voted yes, and the CAs all voted no, except for Let's Encrypt, which had now joined it as a CA. But that meant it failed, because with how the CA browser forum worked, you needed to have consensus in order for this to work. 92% of Entrust, which was one of the largest CAs at the time, customers were on manual processes. They didn't think they could have their customers do this more than once a year, or more than once every 3 years. Then in 2017, Symantec happened. The CT logs, the certificate transparency logs, caught Symantec red-handed, issuing certificates for unauthorized certs. Google caught them issuing a google.com cert. It was the largest CA in the world, and they were issuing certs for domains that they did not own. They were ignoring their own security policies. They had submitted audits from auditors who were not auditors. They were just some guy. They had over 30,000 misissued certificates. Google said, we're just not going to trust you anymore. You're done. Every Symantec, Thought, VeriSign, and GeoTrust, and RapidSSL, which were all their brands, they just stopped working. Google's like, you're done. The remnants of that were sold off to DigiCert because the company went under immediately. The CA browser forum, the audits didn't catch any of this. The CT logs did. Google's own actions, own auditing actions, made this thing revealed. Hot on the heels of that, Google decided in 2018 that, you know what, the way for us to make the web secure is just by shaming everybody who's not, and introduced the not secure label in Chrome. Every website that wasn't on SSL now got this, even SSL, not TLS. Every website that wasn't on HTTPS was now displayed this label that's not secure. Google moved adoption of secure internet from 40% to 97% in the matter of a year. It was the most effective security recommendation or security action that they've ever taken. Making being insecure a thing to be embarrassed about worked way better than making securing things easy. In 2018, modern TLS 1.3 ships, and it reflects all of the lessons that had been learned in the last decade. We dropped 37 cipher suites down to 5, based on a bunch of attacks that had exposed issues. Removed a bunch of stuff from the protocol that was just surface area to be caught, and enforced perfect forward secrecy. You could no longer not use it. Half the protocol had been removed. In 2018, at DEF CON, the term bygone SSL was coined. Has anybody heard bygone SSL? It's this idea that you can sell a domain. If I own example.com and I sell it to you, you own that domain. But I could still have a cert for bygone SSL, or for example.com. Over 1.5 million domains had certificates owned by somebody other than who owns the domain, including stripe.com, which when it was sold, the previous owner had several certificates that did not get revoked and were valid for 3 years after it was sold. The research found that if we dropped lifetimes to 45 days, it would reduce this risk by 95%. The risk being that, like, I have a valid cert, I can pretend to be that domain even though I don't own that domain anymore. In 2019, Google researched that, hey, nobody actually checks that green bar. Nobody actually looks at the company. Nobody looks at that before entering their credit card. They just trust that it's a green. Green is good. So it's not actually any more secure, so they got rid of it. Safari, Chrome, and Firefox all remove the green bar out of their UI. They dropped it. There's no visual difference anymore between domain validation, org validation, and extended validation certificates. No user-facing benefit anymore. So why do they charge more for it? I don't know, but they do. Here's the full scorecard of every major change, vulnerability, and deprecation over 20 years of SSL. Various attacks gutted the thing, but so many of these things caused previous certificates to be broken. Revocation is still broken, and faulty certificates are still around for years. So they tried again. Google and Apple again in 2019 proposed a 1-year certificate lifetime. They go to the CA browser forum and they say, hey, we got to do this. These certs stick around too long. And the same thing happened. The browser said, yes, let's do this. And the CAs said no. 2 ballots. The people profiting off of the status quo had the veto power to stop it from changing. And so here's where it all comes to a head. February of 2020, at the CA browser forum meeting, Apple stands up and says, hey, we're not going to trust certificates over 398 days anymore. Do you want to work in an iPhone? At this point, Apple's big enough that, you know, that's the thing that you can't not support. It wasn't a vote. They just said, we're going to change the rules that we're going to load into iPhones, that a certificate over 398 days will not be trusted. Weird little thing, this is even for private PKI. So if you generate your own certificates, it still doesn't work over 398 days. They just made that rule. We will never accept another one. The CAs complained. This undermines the whole process. You're not getting consensus. Apple said, we can't wait for you. We couldn't wait, like the SHA-1 debacle, certificate transparency logs. We can't wait for this to happen. That was the moment the tide shifted, and short lifetime certificates became inevitable. Here's what actually happened in the wake of that, and what we all have to do about it. That proposal failed. Apple did it anyway. And so they came back in 2020 and said, hey, we need to align things. We need to make everything normal. We need to take all the requirements that we've just unilaterally implemented, and we need to make that part of the baseline requirements. If the CAs block this, the browsers may as well abandon the forum entirely, is what Google said. It's like, you're just gonna we're gonna do this, you may as well make it the rules, or we're not gonna show up anymore. And the risk of that is the CAs would now not only need to be audited once against the baseline requirements, but audited against every single browser's rules individually. The cost multiplication would be devastating for them. So of course, they voted yes, 15-4. The forum survived, it still exists today, but the power shifted. It's not exactly what it was. It's more asking as a courtesy at this point. One of the major factors that enabled this was Let's Encrypt, which the CAs had said enterprises will never be able to handle this. But 10 years later, 60% of all certificates come from Let's Encrypt. 60% of every single one. Millions of renewals happening daily. Acme became a standard. Everybody supports it. The IRS, arguably one of the most bureaucratic organizations on the planet, uses free domain-validated certificates from Let's Encrypt. In 2025, so this is the thing that panics a lot of people today. Apple, Google, and Microsoft come together and they share their timeline for how certificate lifetimes are going to shorten. In March of 2026, which has already happened, certificate lifetimes drop to 200 days. If you buy a certificate today, It's only good for 200 days. Next year, it drops to 100 days. In 2029, it drops to 47 days. The vote passed because they weren't really asking. The alternative was just like they were going to stop going. How does that work out? So a lot of companies are still doing this manually. A lot of companies are still doing this manually. And how it worked right now is 398 days, which means once a year, you had a calendar task to buy a new cert, follow a run book, stick that certificate everywhere you need to go. Now that becomes twice a year, which is like, oh, that kind of sucks. But I mean, you could probably do that. Next year, it becomes 5 times a year. And then it becomes 10 times a year for every cert. Multiply that by how many certs you actually have. At 50 certs, you're doing 500 renewals a year. This isn't just somebody's side job anymore. You need to hire full-time staff to do certificate renewals. The big problem that's left in this space is that automating the renewal doesn't mean automating the deployment, actually getting the certificates to where they need to be. And the perfect example of this was Epic Games last April. They had a certificate expire. Nobody could play Fortnite, guys. They caught it in 12 minutes. The certificate renewed, everything was fine. But full recovery took 5.5 hours and 25 people from their postmortem. It took that long to get that renewed certificate into every single server and device that needed it. They had automated the renewal process, but the distribution was still heavily manual. Getting the right certs to the right servers in the right format, because there's too many different certificate formats, with the right reload command so that everything works correctly. A lot of people who've already tried to implement this, you probably use tools like CertBot or Posh Acme or Acme SH, and here's how that journey has probably gone. Phase 1, you install CertBot. It's a cron job. It does validation. You have one server. It's kind of open to the internet. Everything is done. Easy. Phase 2, you have a Tomcat server. It needs its certificate as a Java key store. Now you have a 50-line bits of bash to do conversions and deployment and copy things around. It doesn't work as good, and now you have to deploy or manage scripting. Phase 3, you have a wildcard certificate you need. Now there's DNS credentials floating around in your scripts. Now you have in phase 4, you have an exchange server or a web cluster, multiple nodes that need to share a single cert. Now you have a shared folder on your network full of certificate files. Despite your best efforts, you still have a 2 a.m. outage. The Nginx configuration was bad. It didn't restart. There was a stale cert. So now you add monitoring. And then security comes and says, who owns these certificates anyway? And now you have a spreadsheet that looks a lot like your renewal schedule with who owns these certificates, who maintains these things. That particular process, which I've seen play out a few times, is why I coined Todd's 10th rule, which was inspired by one of my favorite programming idioms. Any sufficiently complicated SSL certificate script contains an ad hoc, informally implemented, bug-ridden, slow implementation of half of a certificate lifecycle management system. Does anybody recognize what the original of this? Greenspan's 10th rule is basically this, but Lisp. You end up building the same pieces of a system one outage at a time. So if you need to manage certificates in any sort of non-trivial way, you're going to need a certificate lifecycle management system. Something that does discovery, issuance, distribution. I build one of those, but there's lots of them out there. If you want to check out what I've been building, it's at certkit.io. But one more thing. The story isn't over here. Quantum computing is expected to break the Diffie-Hellman exchange, which means that perfect forward secrecy isn't going to be so perfect anymore. The NSA, and probably others, are already recording traffic again, probably, with the idea that once they have a functioning quantum computer, they're going to do this again. NIST has formalized some post-quantum cryptography standards that could hold up against it, but none of them are operational yet. Nobody can really run these at scale. In the next few years, we're all going to have to update this thing again. You're all going to have to generate new certificates. You're going to have to change software. It's all going to happen again. If we've automated, this can become a config change. If you haven't, this could be another 12-month fire drill. This was everything you learned about SSL is deprecated. I hope I shared some interesting things with you. I hope you learned something. Thanks so much for coming. I'm happy to answer questions.